let's continue our study of sorting algorithms by examining selection sort in detail. Here's the idea behind selection sort. You want to find the smallest element and swap so that it's in the first position. Then find the second smallest element and swap into the second position. And you repeat until all elements are in their proper positions. So the way you remember the name for the algorithm here is that we're selecting the next element to put in its proper position. It turns out it's very important to remember the name and the steps in the algorithm and get those things attached together, because that's how computer scientists talk about these algorithms. So you really do need to know that the name of this particular process that I'm describing is selection sort and not something else. Let's take a look at an example so you can see how this would work. The top element of these tables is the array. So the array contains 3, 6, 9, 4, 2, 1, 5. The bottom of the table contains the minimum value as we're stepping across. So 3 starts out as the minimum. It's smaller than 6 and 9 and 4, but notice when we hit 2, 2 is smaller than 3, so 2 becomes the new minimum. Then we hit 1, and 1 becomes the new minimum. Since 1 is smaller than 5, 1 is finally the final minimum. So 1 is going to be swapped into the first position. This means the value 3 that's currently in the first position is going to end up where 1 is. So here's what the array looks like. Now, once 1 has been swapped into that position, it's never going to move because it's in the perfect position. So when we go and look for the second smallest element, we're not going to have to examine the first position anymore. So 6 starts out as the smallest. It's smaller than 9. Then we hit 4, which is smaller, then 2, which is smaller, and 2 remains the smallest because it's smaller than 3 and 5. So now we're going to swap 2 and 6. Now at this point, both 1 and 2 are in the smaller position. If you've been paying attention to what we're doing here, you probably notice what kind of pattern we're getting. This looks like a triangular pattern, and so we know what we expect the for loops to look like when we get around to writing the code. Let's do a few more iterations just to make sure you understand what's going on. Well, 9 starts out as the smallest, 4 is smaller than 9, so it's the smallest for a couple of steps. Then 3 becomes the smallest. So now 3 and 9 are going to swap. So 1, 2, and 3 are now in the final positions. Now this next one is kind of interesting. 4 starts out as the smallest and it remains the smallest all the way along. Now whether we want to do a swap here or not in the method, that gets to be a hard thing to choose. The reason is because sometimes testing to see that you don't need to do a swap is actually more expensive in terms of the computing because you have to do the test every single time, even when you need to do it. Don't worry about this kind of optimization at this point. We can just go ahead and do the swap if we want. So now 1, 2, 3, 4 are in the proper positions. 6 starts as the smallest, 6 is smaller than 9, and we end up with 5 being the smallest. So 5 and 6 switch positions. And now 9 starts out as the smallest and then 6 ends up as the smallest. And so we end up with the array in sorted order. So let's design the loops now. We notice that the outer loop initially starts at the first element and then it proceeds to the end of the array. So we're searching a smaller and smaller number of elements each time. The outer for loop also stops at the next to the last position, because when you get to the last position, the element has to be in the right place. Now, I said a for loop here, and that's usually a good choice for this, because we're sequentially going through an array one element at a time. Let's think about the inner loop for a minute. It starts at the index of the outer loop. That's the triangular part, and it proceeds to the end of the array. The body contains the minimum comparison, and the swap is done after the inner loop is complete. So that really describes the structure of the code very well. Now, if you're wondering where I got that from, I got it by looking at the example and drawing conclusions from it. Let's talk a little bit about one last detail of this algorithm, and that is storing the minimum versus storing the index of the minimum. In the tables that I showed you the minimum value explicitly. That is the thing that was written in the table. But what was implicit in it was where the index was. So when we went to do the swaps, we have to know those indices. Now, it turns out that storing both the minimum value and the minimum index is unnecessary. If you know the index of the minimum, guess what? You know what the value is because you can look it up in the array. So that's a really important thing to realize, is we don't need to store the minimum at all. We can just store the minimum index. This makes the code a little bit tighter, a little bit smaller, a little bit more elegant. If it makes you uncomfortable, however, you're free to store the minimum. Just remember you need to store the minimum index too. So here's the code for selection sort. We're passing in an integer array. As I said, we start at position 0 and go to 1 less than the length of the array. The reason we stop at that point is, remember, we don't have to do that last swap. There's no reason to figure out that the last element of the array is always the largest one, because we know it has to be by that point. So we let our min index initially be start, and then we start the rest at start plus 1. So we don't have to make a comparison between start and start. Doesn't make sense. Stopping at the end of the array. So all of these are things that I got from those tables that I showed you earlier. If the data of the min index is greater than the data of the rest, well, that means that the rest is the new min index. So that's what's done in the inner body of the loop. After we get to the end, then we do a swap between data of min index and data of start. And that's what puts the value into the position. So notice this is very tight, small code. It's really not very hard to write, and this is a pretty darn good algorithm. But let's talk a little bit about the story of sorting. First off, it's a very old problem in computer science and a very common one. The reason it's old is we immediately realized in computer science that if we could put things into sorted order, we could find things more quickly. So very, very early on, this became important. The interesting thing is that it's sort of like a graphic novel. It's kind of exciting. So we have these very simple algorithms. For example, selection sort is one of the simpler algorithms, but they tend to be inefficient. There's an algorithm called bubble sort that is absolutely the worst. In fact, it's so bad I don't even teach people to do it anymore. If you want to learn that algorithm, you can look it up in Wikipedia. Just remember, I don't approve. So, it's a very simple algorithm. You can implement it correctly. It gets used all the time. I have to admit, as a professional software engineer, when I see somebody using bubble sort, I sort of demote their skill in programming by a level immediately because it's just really so bad. Then there's our hero, which is quicksort. And quicksort is great, almost always. But there's this problem. It has what's called a tragic flaw in literature. So, for example, if you've read about Oedipus, his tragic flaw was being so clever. It led him to try to be clever when he shouldn't have been clever. Well, quicksort is like that. Quicksort is our hero with a tragic flaw. Generally, it's the best algorithm going, but every now and then there's a case where it behaves really badly. In fact, it can behave as badly as bubble sort or selection sort. So that's a pretty big tragic flaw. Now, it turns out that merge sort is an algorithm that's the best in theory. So here's our hero, right? Well, but this one has a tragic flaw too, and that's that it requires twice as much storage space. Now, both quicksort and merge sort use a programming technique that's beyond the scope of this class, so we're not going to learn them. It's kind of interesting that there isn't one right answer. As much time as we've spent working with this problem and trying to solve it, we don't have one answer. So what it means is that we need to have some tools to understand this. And we don't really know what these tools are just yet, and we won't know by the end of the semester. But this is what makes sorting a really interesting problem, and it has a really great story. So keep programming.